faces, so good to see lots of folks. John, Mitchell, Justin, good to see you. Just talked recently. Yeah, a lot of familiar faces and some new ones as well. So we'll give everyone just a quick second to get in. And I prepared for a longer session, so maybe I'll try to go through my slides a little bit quicker just to leave a little bit space for dialogue. But let me introduce Coreshell, hopefully within the next 10 minutes or so, and then leave opportunity for activating discussions and participation from the crowd, because I think that's really what's going to be more interesting. So our talk, as we mentioned, was about how silicon is our best chance for a low-cost US-based lithium-ion battery, and something that can actually replace Chinese reliance from both a unit economics and scale perspective. So that's what we're going to be talking about today. Just a really quick intro to our mission. We wanted to make the world's lowest cost high performance battery, right? And I think that's really not what people think about when they think about silicon. So we're really trying to change people's minds about what the benefits of a silicon nanotechnology can be. I think it's really spent too much time classified as this high performance, highly engineered substance that can add range to your vehicle. We don't really think people have taken advantage of the fact that it starts at a lower cost than graphite and has 10 times its specific capacity, which can really lower the cost of your vehicle rather than increase the range. So that's really how we approached it. Quick intro to our company. We've got about 45 people. We've built a pilot production facility, so I'm excited to really demonstrate that this is a near-term possibility, not just something that's in the future, 10 years plus of R&D. We're scaling this and commercializing this now. I won't spend too much time. That's pretty self-explanatory as well. So again, our goal, replacing graphite. Our competition we see is really Chinese graphite.
I can't hear. Everybody else can?
Me either.
I can't hear.
Can hear you.
Oh, we just lost him.
Hey everyone, I got kicked out. So I'm going to go against protocol, and I'm actually going to turn off my video because I think my internet bandwidth is not the best here. So if somebody could please let me know where my audio and video stopped, I can hop back into the presentation, hopefully.
You're talking about the replacement of graphite anodes with silicon.
Thank you, Justin. Hopefully this will work better with my video off, and then yeah, I'll try to get through a few more slides quickly so that people can get the gist of it. But yeah, we feel like, again, silicon has the property of being lower cost. If you look at commodity price silicon, it is lower cost than graphite. And it has 10 times the capacity.
Jonathan, can you hear us?
Oops. Apologies for that. 1 second. Okay. Thanks everyone for sticking with the technical difficulties there. So yeah, again, we want to really take advantage of that. The other thing that I think silicon provides in a lot of abundance is a supply chain benefit as well. So in addition to being something that can be a replacement for graphite on both a cost and material basis, silicon also has the largest production volume of any anode material in the US and in Europe. So the panel is really relevant today, talking about how it's really hard to develop mines and assets, and it takes 10 years to really get those things off the ground. We don't have to do that with silicon, as opposed to graphite or even lithium metal or those sorts of resources. We have mines already here in the United States. That's part of the reason why we've been excited to partner with Veriglobe, who is the largest producer of silicon in the Western Hemisphere. So they're proof of this. They own mines in West Virginia, in Alabama, operational already. So just want to emphasize this is an already industrialized raw material supply chain, and something that we can tap into immediately, not something that we'd have to develop for the long-term future. So I think what we have really developed at Coreshell is, again, tapping into not just the energy density benefits of silicon, but tapping into the cost side of things. We believe that pairing it with LFP, which is an unusual pairing, really brings the best out of both, right? Something that can get LFP closer to the energy densities than MCs, but something that can be actually much lower cost than both, even lower cost than LFP graphite. So we feel like this is the pathway that's necessary for competing against cheap Chinese products while built here in the United States, and still having the supply chain to do so. So that's our argument for why we feel like silicon is really the best for doing so. It's also got the lowest CO2 footprint, which is nice for sustainability reasons, which I'm happy to still say, even though administratively I think that's a bad word these days. But I still think it's important. It's the reason why we started Coreshell. So I'm not going to go into the performance, but safe to say we've demonstrated good cycle lifetime, good charging capability. We've solved the swelling metrics with this type of silicon and shown that after hundreds of cycles, it's a pristine anode. So if anyone's interested, we can show that afterwards. The other benefit of pairing with LFP is that we've demonstrated that it can be as safe as an LFP graphite battery as well. So you can have the energy density of an NMC, the safety of an LFP, that's even cheaper than your LFP graphite cell. We feel like that's a major market winner. And we're demonstrating it at scale now. So we're producing 60 amp hour cells. We've got a lot of automotive customers that we've been working with. And we feel like, again, this is ready for near-term commercialization. Cool. So I will stop there in terms of my presentation, and really kind of open it up to the forum so that we can have more participation and get people talking. And maybe actually I'll do this. I'm going to stop sharing. Daniel, are you on the call today?
I am.
Great. Maybe you can share your screen so that I don't have to take up the bandwidth for my Zoom, and we can have a little bit more of an active discussion without having to deal with my crappy hotel internet issues.
Sure thing. Let me get it pulled up.
I want everyone to know I did pay for the gold platinum internet package, so this is as good as it gets here. So we are trying to do what we can.
Where are you, Jonathan? That's the question.
I'm in Munich right now. So just flew in this
Oh.
morning, and hopped on the call.
Okay, awesome. I was expecting better internet quality and Munich, but have fun.
Yeah, it's funny. In the Western world hotels, I feel like the internet is particularly bad. So while Daniel pulls up those slides, maybe I'll posit to the room. We obviously made our case for silicon as being the best anode direction that the US should invest in for its future security and supply chain. There's limited resources and opportunities to invest in these types of activities, so we can't go and do this for everyone. So I'm curious to hear if anyone has an alternative pathway they'd like to propose. If anyone here is working on lithium metal, if anyone's here working on different anode materials, would be happy to hear what other folks think about the direction of getting anodes built here in the United States. Anyone want to take a stab at that?
I have kind of like a question and answer. So I feel like whatever anode material is going to come on board depends on if it's like a drop-in solution, how well it can be, how well and fast it can be integrated with the current battery chemistries and manufacturing processes. So I'm not sure, maybe I've missed if you talked about it. Like, for example, if I am an LFP manufacturer and want to like use your anode material, do I need to change anything in my battery design or chemistry?
It's a great question. I think that's an important consideration. And that's part of the reason why we feel like silicon has maybe one key advantage over lithium metal is that you don't have to change your manufacturing process to silicon, at least for the type of silicon. So we're producing a silicon anode powder. Part of the reason why we've also continued to scale our cell manufacturing. And Daniel, you can kind of go back a couple slides if you want, or just one slide. We are building 60 amp hour automotive size cells using right now a standard lithium ion process. People can come and audit the equipment, go take a look at the entire process. We're using an aqueous-based slurry process. So no changes to the manufacturing equipment. I hate to say the word drop-in because honestly, any chemistry requires some consideration from process development and slurry development. So even changing graphite requires that, to be honest. But I think this is about as drop-in as you can get. So I think that's really important. Not changing manufacturing. Changing manufacturing is really challenging. I think that's something that a lot of people underestimated in terms of the difficulty of integration in new technologies is what effects is it going to have on the large scale manufacturing? We've spent so much time really going down the learning curve or going, down the cost curve of lithium ion battery production. The equipment has gotten so fast and so efficient. To redo that process with something else, I think is going to be challenging. So I don't think it's impossible, but I do think that in the near term, let's say in the next 10 years, it is going to be challenging for other, I'll say for chemistries that are not built using the same types of equipment that we're using today. Yeah.
Yeah, that's great. I think that's exactly what separates Coreshell from other manufacturers. Like we work with a lot of startups, and actually I'm writing an article about the path to domesticating battery supply chain. What I see, which is I don't even know if it's realistic, is like sequestering carbon and using it for like graphite. Which I don't even know if technology is feasible or if it is, like how many 10 years it's going to take to come on board. And the second thing I see a lot is like just coming up with new chemistries and like moving away from lithium ion. So in my radar, I haven't seen anything close to what you're building. So kudos to you.
Thanks, Sama.
Mhm.
I appreciate that. And for context, we know Sama, so she's already very familiar with Coreshell and our technology. So we appreciate the plug for what we're doing. And I think you're exactly right to kind of point out the scale of the material supply chain is also something that we consider to be very important. Being able to satisfy the scale of electrification of vehicles in the next 10 years from a raw materials perspective is pretty it's a pretty big consideration. I think that's I'll just mention one of the other reasons why we have gone to a silicon dominant, and actually our plan is to go to 100% silicon anode. So replacing all the need for graphite. Instead of just being, an additive, right? A 10%, 15%, 20% additive that gets you more range. We're trying to look at things in a much more holistic manner. And I think somebody asked for some cycling data. So we can show that we've gotten for an anode that has almost 100% silicon, above 93 or 94% capacity retention at 500 cycles. Daniel, you can go back to that slide if you want. I think it's in there. So this is stuff that automotive companies have verified for themselves. We've shipped this out. It's in a 5 amp hour cell configuration, multi-layer pouch cell. So yeah, and still we're not going to be blinded to the fact that there's still obviously more product development that we're going to have and more improvement they're going to need to get into full automotive. But this definitely shows that it's plausible and possible to get there in the near term, not something that's a 10-year project away. Okay. Well, maybe we can move on to the next question then, if nobody wants to kind of propose another
I have
anode.
one more question, Jonathan.
Oh,
I
sure.
mean,
Go ahead.
yeah, it's great that you are collaborating with Ferroglobe. Do you mind to a little bit comment on the size play a key role in your slurry? How do you manage it in the size that is uh, uh, your process is capable all the time? You are keeping it as constant.
The size of the particle, is that what you're
Yes,
asking about?
yes.
Yeah, it's a great question. I think it's in there, Daniel. It's probably in the appendix slides. We show a cross section of our anode material. Yeah, there you go. So we're actually not controlling for much narrow size. I think that's also important. Mechanical milling only gets you down to maybe a couple of microns in size. Anything below 1 micron in size, really you're talking about exotic techniques to get there. Talking about nanosizing particles, laser ablation, very difficult and challenging technologies. And so I think our cutoff was, what can you get with a traditional jet milling or mechanical milling process, taking that as our starting point and going from there. So you can see that that's kind of the proof here. You can see that the particles are not homogeneous in size. There's a distribution to them. They're not engineered, so they're not a highly engineered shape or spherical. So that's our goal, right? To process that silicon as minimally possible, and that allows us access to the largest base of materials, right? We can use Ferroglobe's already industrialized material base. They're already producing commodity silicon at hundreds of thousands of tons. If you start to go into much more processing, then you're starting to move away from commodity to specialty chemicals, right? Then you're starting to move into smaller and smaller streams. Yeah. So it is to us important to keep it as basic and simple as possible.
Great, thank you.
Yeah.
So Jay has a question.
Yeah, well, it's more of a comment and in addition to what you've been talking about. We are not a battery company. We're an electrolyte solvent company. We're doing inorganic liquids that are not ionic. It's a pure liquid. And David, Jonathan, we've actually had some really good experience with silicon anode materials, starting with a 30% silicon graphite with a nickel-rich, more than 811 cathode. We demonstrated out to 620 cycles at slightly better than 85% capacity with our additive, well, it's not an additive, a solvent at 17%. We've also shown some good cycling performance at 100% silicon that we're still waiting to see where it goes after 500 cycles. So one of the things we've actually learned is that all silicon anodes are not created equal.
That's true.
It depends on how you've made them. It depends on the composition. And to a great degree, the formulation of the companion electrolyte needs to be, at least in our experience, needs to be modified depending upon the actual silicon anode itself in order to maximize the performance of the anode.
Yeah, agreed. That's the reason why we've been demonstrating in a full cell, Jay. I completely agree with you, which there is really no such thing as a like for like drop-in replacement, in my opinion, in lithium-ion batteries. The whole system kind of works in a sort of complete package, right? Exactly right. We're using, for example, a pure silicon. That's going to be very different than a silicon carbon or an SiO product. The chemistries, the reaction against the electrolyte is completely different. The surface chemistry is completely different. And so what we are working on is it is demonstrating the whole package. Long term, we want to be a silicon anode active material supplier. We don't want to be a gigafactory producer ourselves. But we think it's important to demonstrate at a full cell level in a representative cell that can be manufactured at a reasonable scale. Because otherwise, you're trying to convince a very mature, now more mature industry that's built up at scale to take on a chemistry risk. That's really not going to be something appetizing for them until you've de-risked it to a very large degree. So completely agree with your assessment.
That's why we're only talking about data as it relates to full cell applications. And frankly, we've had the experience with Department of Defense contracts where we've been able to apply what we're doing with silicon anodes in a deliverable, and therefore have some real data and real battery experience. So we should talk.
Yeah, we'd be happy to talk. We're always open to collaboration, and we also have been working with the Department of Defense. So hopefully there's kind of
And we're
some,
also USA. We're also USA made.
yeah. No, I think it's important now to continue to build that supply chain. Yeah, and I think electrolytes is definitely something that
It's often overlooked.
is that correct? Maybe you can kind of say it for us instead of me trying to pronounce it.
Oh, I lost you for a moment, Jonathan. My name is Bhamiti, and I'm a postdoc with the University of Kentucky Center for Applied Energy Research. Great work, but I have a question on the product, like the cost of the graphite LFP chemistry and your silicon graphite and LFP chemistry. So you say that there's a 17% cost reduction for as compared to graphite LFP chemistry in your case, right? Is it the battery pack cost? Does it include the production processing and the overall cost of the battery, like from start to end, or is it like, did you get my question?
Yeah. No, it's a great question. I
Mhm.
wanted to make
Mhm.
sure I
Uh-huh.
gave you a chance to ask it.
Mhm.
So it's an important question. This is a summary slide of something that Roland Berger, who's a market analyst, put together for us.
Mhm.
So first and foremost, we felt like this was
Mhm.
such an important thing. We didn't want to do the
Mhm.
analysis ourselves. We wanted a third party to verify this analysis. This
Mhm.
is what do you call a soup to nuts evaluation of the entire battery cell manufacturing, right? Just the
Okay,
cell manufacturing.
I
But
see.
you can, if you want, we're happy to share this offline. It's a 50-page report that they put together that includes the
Mhm.
material inputs, that includes the
Mhm.
cell design, that includes the manufacturing of both the cathode and anode. It includes the
Mhm.
whole process. And I think somebody asked in the chat, what about the LFP side of things? How do you pair that with the LFP? So we are
Mhm.
trying to make that LFP as thick as possible. And one of the things that Roland
Mhm.
Berger did is said, okay, if
Mhm.
you're making such a thick LFP, we're going to give you a little bit of deduction on the processing of that LFP because we think it's going to be slower than your traditional conventional LFP. And we said, great, put that in the report. We're happy to take that as something that is possible for the large scale manufacturing of it. We still feel like it's going to come out in head. And it's very simple, right? Silicon, if you can get it even close to the cost per kilogram of graphite, it's got 10 times the specific capacity, right? So you can use 10 times
Mhm.
less material.
Mhm.
There's just such an inherent advantage that brings to the table from a cost perspective that we feel like that's been underutilized in the space right now. As opposed to, just thinking about the energy density, think about the materials utilization and how much lower amount of materials you can use. So, and then from a pack perspective, that's why we wanted to show the safety aspects, right? If we can make this as safe as an LFP graphite, then from a pack level perspective, you're actually gaining even more advantage against NMCs because you have less thermal management, you have less of that, packing density that you have to spend on those things. So we're showing this again, large format cells, and we're going to show the safety of an LFP graphite. I think that's going to be really key.
I see.
Okay.
Thank you, Jonathan.
Yeah. Haidar?
Yes, hi. Thank you for your talk today. So I have slightly different question, kind of looking into the distribution issue that as you show in the electrode. Does Coreshell consider, for example, dry process manufacturing of electrode? Since, for example, the slurry made electrode has this distribution issue. So it may not have that with a dry process made electrode.
Yeah, it's a great question. We have not tried to integrate dry electrode, taking on one challenge at a time. Replacing the chemistry from graphite to silicon is let's say it's a big enough challenge for us that we don't want to add more complexity to that. I do think that a lot of people are very much interested in the dry electrode process. We've talked to our customers about this. It's less important for the anode than it is for the cathode, right? Because the anode side, it's an aqueous process. So we've already demonstrated this is made using aqueous anode slurry process. Getting rid of water is not, I mean, it's nice, but it's not the biggest deal in the world. Getting rid of NMP on the cathode side is a much bigger deal. And actually, we're interested in pairing our stuff with a dry electrode LFP because actually dry electrode is better at making thicker cathodes. So that actually may even bring even bigger advantages. So we're using conventional technologies right now, but I think in the future we can even take advantage of that dry electrode cathode process to make this even more energy dense. Because that's a limiting factor right now. It's not the anode. We can make the anode super thin. We actually can't make it thin enough to pair with something that's thick enough on the cathode. So we can't make the cathode thick enough. We can't make the anode thin enough. So we're really limited by the cathode side. But yeah, it's definitely something that we're interested in.
Thank you.
Yeah. Anderson?
Hi, Jonathan. Don't mean to keep you on this topic for too long, but just in terms of anode directions, just wanted to get your thoughts on this metallurgical silicon versus emerging technologies such as anode free, not necessarily lithium metal pre-plated onto the foil, but just like carbon coated aluminum or carbon coated copper and plating stripping lithium. I think I read something like CATL has like an auxiliary battery. It's not as high cycle life, but it's developing just in terms of that direction going in energy density. Anode free is really high. So I wanted to get your thoughts on how those two can compete.
Yeah, actually, I completely agree with that. We've I think talked about this during conferences. We feel like the only way that lithium metal is going to be really viable is the anode free option, because I do believe that that is enough of a significant change. And I think one of the biggest bottlenecks right now is exactly right. There hasn't really been an industry that's been built up on high quality control lithium metal foil. It's actually very difficult to process, extremely sensitive, and it's like working with, I think people are quite just like, stretching gum out, right? It's just really challenging to work with. So I think anode free is the option. And, it's funny that CATL announced that. I mean, they basically copied essentially what Our Next Energy was doing with their sort of dual chemistry. You're right. If you have a dual chemistry pack and you can have one that only lasts for 200 cycles. Maybe there's a market there for some, lithium or anode-free cells. I think there is a market for that. That's a great point. We talked about what other options can we explore. I think that is one of them. And I think there's going to be enough room for multiple, key technologies in different segments. And to me, it comes down to the vehicle, right? We already mentioned we're pairing with an LFP. Our goal isn't range extension, right? We're not trying to get to range extension. We're trying to get the volume car market and an affordability and profitability point that can sustain the industry. So we're happy to work on that market and have others tackle the challenges of maybe pairing with a range extension or getting some, exotic chemistries that go out there. To me, I think you're exactly right, Anderson. I believe, in my opinion, this is just me speaking, not for the market. I believe that anode free is one of the few alternative pathways to getting somewhere. Versus, I'm much more of a believer in that than lithium plated lithium metal cells.
I see. So you're saying like the difference between anode free and silicon is still in the cycle life, where anode free is something that would extend the range versus silicon can actually cycle up to the needed ranges or the needed cycle life for EVs.
Yeah, I still think anode free has a long way to go, at least from what we've seen. Still has a longer way to go. You're also pairing it. I think you still need to pair with the solid state battery, and the manufacturing integration challenges there still remain, right? So I think there's going to be more challenges to getting that economical at scale. And the technology, I think, still needs to be proven out further. But I do think that is a viable pathway and should be explored. We just feel like for our target market, which is again volume segment, entry-level cars, we feel like silicon is going to have a much better chance of doing that than an anode-free chemistry at the moment.
Makes sense. Thanks.
Yeah.
Jonathan, I have one more question. It's okay.
Sure.
You have shown very great data with the 500 cycles. It's almost quite 90% stability. Would you be elaborate? How do you, for example, like carbon material playing a key role on your silicon, or how do you? Generally, we call it as it's a Coreshell's with a hard carbon, or afterwards any particularly CNTs or like graphene has a role to play, or are you because it's a very good data from your end. It's very stability. That's why it's very curious. How do you mind very generally elaborate without any confidential?
It's a great question. Yes, we do have carbon in the anode, so it additives and right, you still have to have those components in order to make it a functional anode. Especially, as people know, silicon is not as conductive as graphite or carbon, right? So you definitely need some of that carbon content there. But we're using, commercially available conductive additives. We're not loading it at a super high level. So we've talked about this before. It's publicly available data. We're using 90% active material and 5% conductive additives and 5% binders. That's a little bit high in terms of percentage than conventional, but you have to account for the fact that our anode is so thin. So on a per material basis, we're actually reducing the carbon additive and the binder content significantly. Again, we're trying to stay within the limits of manufacturing standards, unit economics, and profitability. And yeah, we agree. We think the results are starting to become promising for making this a really viable commercial battery.
Great, thank you.
It's actually, commercialized and ready for many markets. We believe that it'll be near-term commercialized
already
for
giving
electric
your customers, the automotive customer. That is a great success already to going on a higher loading of silicon. Because I work only for like a 25%, not this high. That's amazing.
Yeah, agreed. And I think a lot of people agree. Justin, do you want to ask your question?
Yeah, I noticed that the carbon particles that you have in your anode are quite large. Do you think there's opportunity to get your dispersal with smaller carbon particles and thus better conductivity?
So those are, so that's a great question. The conductive additives don't really show up in the diagram because they're too small. The large particles that you see here are actually the graphite. So there is still a small amount of graphite they're adding to it. So we haven't gone 100% our way to 100% silicon yet. That's the plan for the end of this year. But there is still right now we're demonstrating it with 10% graphite right now. So that's what you see as the large particles. We don't know how much of a role that's playing. So again, we believe we can go to 100% silicon of the active material. There is still 5% additives. So that's I'm kind of the belief that we should be able to get to a graphite-free system because as people have mentioned, it's not like it's distributed that well in our electrodes. So and it doesn't really participate in the electrochemical process. So hopefully that means that it's not that critical of a component for us.
Thank you for clarifying.
And I think for oh yeah, sure. Last question, because I think we're at time, so I want to be mindful of people's time. But Raghav,
Yeah,
question?
couple of questions. Are you licensing out your technology and are you making it licensing friendly? I'm in India and I wanted to have an offline conversation with you on licensing. And the other is that have you checked out recycling sources for your silicon anode? These two questions.
Yeah, great question. We're not planning on licensing the technology out at the moment, but we are open to in different regions to please definitely contact us and hopefully we can have a conversation offline. And then the other thing you asked about was now I'm blanking. The second question,
Recycling sources for
sorry,
silicon.
Raga, maybe you can remind me what the second question was again.
Recycling sources for silicon?
Recycling sources for silicon. That's right. Yeah.
I think Wi-Fi is quite bad, Jonathan. I think
I think
certainly. Okay.
Yeah. Yeah. I think that's Wi-Fi on my side. We have not explored recycling sources yet, but we feel like we have a very large basis already, but we're always open to it if the unit economics make sense. Okay, well, since my Wi-Fi is terrible, I don't know if people can still hear me, but okay. Since my Wi-Fi is pretty terrible as it is, hopefully this is actually a good time to call it. And yeah, I want to thank everyone for joining today. Appreciate everyone's patience as we well, as I dealt with Wi-Fi issues. And if anyone wants to learn more, please definitely reach out, contact us, send something through the email. And I promise I'll get on a Zoom line with better Wi-Fi if we have a conversation in the future.
Jonathan, what is your